All right. Thanks, Sean. So yeah, today I am going to be talking about an ongoing survey of hot Jupiter atmospheres that we are doing with Keck that Jerry alluded to a bit earlier. And like Jerry, I'm going to start out with a version of the exoplanet mass separation diagram, except that Jerry's targets that he was interested in would be way over there beyond the far wall. Whereas I have focused this plot on planets in a mass range that suggests they have a large gas envelope and at separations substantially inside the orbit of Mercury. So there's a bunch of interesting things happening just on this diagram. I could spend 5 minutes on this diagram. But the thing I want to point out is there's a lot of diversity here, and we have no examples of these planets in our own solar system. So every one of these planets is an example of a radically different outcome of the planet formation process. So if we want to understand how Earth-like planets form, how solar systems like our own form, understanding this counterexample is actually really important. And so as Jerry mentioned, if we want to understand giant planets, we want to understand their formation, there's two general pictures that this falls in. There's core accretion, which is sort of a two-step process. So when, where, and how the second step happens impacts the composition, or there's a direct collapse that produces a planet of roughly stellar composition. But if we want to form hot Jupiters, we don't just need to form a gas giant. We need to form a gas giant and then get it right next to the host star. Generally, the way that's popular to do this is migration theories. Either some sort of disk migration where interactions between the planet and the disk send the planet inward and the planet can continue to accrete over this process, which can change the composition. The alternative is after the disk is dissipated, some three-body, multi-body interactions can scatter planets inward and can produce very tight separations and very high spin orbit misalignments. So to figure out what's going on, people have been looking for chemical tracers of planet formation. What is the chemical imprint on the atmosphere of the planet formation process? And the classic work in this is this Oberg, Clay, and Bergen paper, where they basically looked at the impact that snow lines have. So as you go further out in a disk, different materials freeze out, they become ices. So the dust, you increase the dust mass, you decrease the gas metallicity, but the C to O ratio, of the gas continuously increases. So this potentially tells you metallicity and C to O where a planet got most of its gas envelope. Now, in the 12 years since this, there's a bunch of other things we've started to consider. Snow lines aren't step functions. There's a lot of sort of complicated behavior that happens near snow lines. Solids can drift from one part of the disk to another. That can change what the solids are. We have to think about what is the solid to gas accretion ratio? Is that constant over the whole planet formation process? Is that location dependent? And so the predictions that have come out from sort of these further iterations is that for core accretion, we expect an inverse correlation between a giant planet atmosphere's C to O ratio and its metallicity. And we've also identified a bunch of other interesting potential tracers of the planet formation process. That really suggests if we want to understand these planets, we want to understand their formation, we want really detailed chemical characterization. Now the challenge of doing this with transits is that you get two lines of sight. You get the morning terminator, you get the evening terminator, and you get a little bit more from the rotation, but it's not all that much. And then planets are 3D, so we can have things like dissociation on the day side, rain out on the night side. Then maybe there's winds that blow these day-side dissociation products around to the other side of the planet. And then maybe we have clouds. Maybe these clouds result in a flat transmission spectrum. Maybe the clouds preferentially occur on one limb and then make deconvolving these different 3D effects really difficult. And the other issue with relying solely on transit spectroscopy or even secondary eclipse spectroscopy like James Webb does is the number of targets that you miss. You need a really precise orbital alignment to do this. So you're missing, even for hot Jupiters, 90% of planets. Most of the brightest exoplanets are non-transiting. So we would really like to be able to characterize those planets, which are otherwise very amenable to characterization, except for this orbital misalignment. So we can treat hot Jupiters as binaries. The problem here is stars, even in the infrared, are a few thousand times brighter. But we're not looking for a photometric 1 part per thousand, 1 part in 10,000 effect, right? If you have near spec, a planet spectrum looks like this, right? You have dozens of resolved carbon monoxide lines near the CO band head. And then if we think about observing for 3 hours after secondary eclipse, the planet's projected radial velocity shifts by 100 kilometers per second, which is something, this is the near spec velocity resolution, so that's really easily resolved. And so this makes this much more tractable to do for hot Jupiters. And the way that we do this is KPIC. As Jerry described before, the idea is we have a single mode fiber feed that goes into near spec. The benefit that we're using for hot Jupiters is that this interface is extremely stable. You have a very stable line spread function over multi-month timescales, very stable wavelength solution and Blaze function, so you can really look at these minute changes as these weak planet lines shift in radial velocity. So this is an example from a paper we published earlier this summer where we did this for WASP-33b, which is an ultra-hot Jupiter. The y-axis here is time, the x-axis is velocity, and we've basically taken a model of the planet atmosphere and we slide it across our data set at a range of velocities, and then the color is a goodness of fit parameter. When the planet's blocked by its star, it's in eclipse, we don't see much, but then when the planet comes out of eclipse, we see this line that roughly traces where we expected to see the planet's radial velocity signature, and when we shift to the planet rest frame and COAB, we get this really nice peak. And then because we're directly detecting planet lines, we can iterate the model we used to do this, right? We can do basically a atmospheric retrieval. We can get the pressure temperature profile, we can get abundances, we can get an idea of what the actual spectrum looks like. So for WASP-33b, this gave us a C to O ratio that's pretty high and a high metallicity, which right away contradicts that sort of core accretion prediction. We saw a very similar composition for WASP-189b, which is another ultra-hot Jupiter. The challenge for both of these is that dissociation can bias the abundances in some of the hottest planets, so that's somewhere where we're looking to improve our retrieval pipeline going forward. We've also looked at colder planets. So this is HD 189733b. This is a Jupiter mass planet with an equilibrium temperature of around 1200 Kelvin and a K2 host. So this is a paper that we'll be submitting hopefully next week. We looked for 7 different species. We make good detections of water and CO, but we place pretty stringent upper limits on methane and ammonia, which rule out the equilibrium chemistry models we were looking at, and also some of the photochemistry models. So they're now actually looking quantitatively at photochemistry in these exoplanet atmospheres. Here, when we look at the C to O ratio and the metallicity, we get a substellar C to O and a stellar or superstellar metallicity. For this target, we have very good stellar abundances from, I think it's the Keck Abundance Survey, which if Alex Plansky's here, thanks. Yeah, that paper was really nice, really tight error bars. But it lets us say something about the composition of the planet relative to the host star, which is that potential indicator of planet formation. And we're also, what's interesting is seeing signs of 13 carbon monoxide enrichment as well. So based on this, we've begun a larger survey. We think that Keck and KPIC can characterize about 40 hot Jupiter atmospheres that spans a really wide range of mass and insolation that's reflective of this population as a whole. So our hope is that we can actually, at a population level, understand what's happening with these atmospheres, what is the underlying distribution of these processes that we think trace the planet formation, and can we map that to some sort of formation history for this population. So we have 10 detections so far, 1 more that we're working on. I'll just highlight those real quick. This is pre-2023A. There's 4 unique detections. The idea here is that the dashed red lines indicate the planet rest frame. So ideally, we see a nice peak that indicates the template is a good match at the planet rest frame. So we get that. 51 PEG B, we think we have. It's non-transiting. You can do this for non-transiting planets because you're looking at the thermal emission spectrum. Kelt 9, we have maybe that's the planet, but it's much weaker than expected, and we think that's because this planet's so hot, there's a much stronger thermal dissociation effect happening. I do want to highlight you can use KPIC for transmission spectroscopy. Our pipeline is not as developed to do this yet, so this is sort of a quick look. There's a number of effects we know about that we haven't accounted for, but we do think we have a detection. It's offset from the expected rest frame, and we think that's probably due to some combination of winds and rotation. So we're going to look at improving our modeling there and seeing if we can make a more definitive statement. We continued the survey in 2023A and then lost about a third of our time to weather. The winter was pretty rough on Mauna Kea. But we still made 6 detections, and there's one more that's in progress. So we are continuing. 2 that I want to highlight are HD 149026b. This is a Saturn mass hot Jupiter that the JWST secondary eclipse spectrum claims is 200 times solar metallicity. So that's pretty amazing. We have a nice K-pic detection, so hopefully we'll be able to see if that really metal-rich atmosphere is consistent with what we're seeing at higher resolution. And the other thing I want to highlight is our near real-time quick look capability. So this is TOI 1518b. The planet it's an ultra-hot Jupiter, not that different from the others, but what I want to highlight is that this plot was done before Matt had finished closing the telescope at the end of the night. I had been downloading every 10 frames and rerunning our quick look reduction and our cross correlation, and I saw this grow from 2.5 sigma to over 6 just as we were doing this. So our pipeline for detection is mature, it's fast, trying to get that to extend to the retrievals as well, which is a bit more of a challenge, but we are hopeful that we are moving on to that now. So I'll leave you with this last slide. Our goal here is a population-level understanding of hot Jupiters. What is the underlying ratio of, or underlying distribution of C to O of metallicity, and what can that tell us about the processes that led to the formation of this population? Along the way, we're also going to get a ton of information on winds and circulation that will let us actually test global circulation models in the hot Jupiter regime. We'll get information on what kinds of photochemistry are happening, where in this parameter space photochemistry is happening, and the carbon isotope log ratio, which is interesting even if we aren't quite sure what it means in terms of formation just yet. So K-pic was off sky in 2023B. We're going to take that time and further improve our retrieval pipeline, but we hope that we can have a sample of 20 to 30 objects by the end of 2024B that will let us really make a statistical claim on these topics. So I will stop and take questions. Thanks.